Hello. So looking at another dynamic programming problem. This problem is called coin change problem. And the problem says, given a coins of different denomination, we want to find the number of coins that add up to a given amount, right? And so if we take this example, coins 1 to 5, and we want to get the amount 12, by doing 5 plus 5 plus 2, we get 12, which means we get 3 coins, right? And so this is what the problem asks us. We get a list of coins, or coins of different denominations, and we get an amount. And the goal here is to find out, using these coins, what is the minimum number of coins that we can use to get that amount, right? And so the first thing that you may think is, okay, I can just do a greedy approach because it works with this example, right? Just take the largest coin first and keep taking it until, as long as you can, when you subtract it, it doesn't give you less than 0, right? So for example, here 12, we can still take 5, and so we have 7 left, so we can still take 5, which is the largest coin. So that would give us left 2, and so we take 2, and we have 3 coins, and that's actually the answer. That's the minimum number. But if we take a different example, like 1, 3, 4, and the amount is 6, and we try that. So the largest one that we can take is 4. So we put 4, and then after that we are left with 2. We can only take 1, so we take 1. After that we are left with 1. We can only take 1. We take 1. So we get 6 with 3 coins. But actually that's not the optimal answer. The optimal answer is just take 2 3s, which gives us 6, and it's 2 coins, right? And so with when you think of a greedy approach and you find a counter example, that's actually enough to know that the greedy solution won't work. And so here now we are left to think that, okay, there is no way for us to know in advance the answer here, right? We have to try different possibilities and take in the coins in different orders and see just which one is better, right? So that directly means doing dynamic programming, and that's what we'll be doing next for this. Okay, so let's see how we can solve this using dynamic programming. We'll start out first with using a top-down approach, right? And so for that one, what do we need to choose? It's the easier way to solve it. We will use a recursive, basically just using recursion and memorization. So for this, what do we need to find? We need to find a couple of things. First, we need to define what is our base case. And we need to, of course, find the state of the function that we will be recursing on, right? And then we will also need to find, like, what is the recurrence or the recursion that we will do. And those are the main parts that we need to identify. First, let's just look at the state. What is the state that we'll be using? Well, we have an amount, so we have, let's say in the example, we had 1, 2, 5, right? So for that one, and then we had the amount was, let's call it n, was 12, right? Or let's call it maybe the x. So at each point, we want to try all of them, right? So we want to try all coins first as the first coin, right? So try 1, and then try 2, and then try 5. 5. So what this means here is that, well, we are left with x equal to 11, and the coins become just, well, we still can use all of them, right? Because we can do repetitions, right? And so here, x will be equal to, it will be 12 from 2, it will be 10. And we can still use all the coins. And so since we can still use all of the coins, that means that the state doesn't change, the coins don't change for each state, so we don't need them. So what this tells us is that the state that we will need is just the value x remaining, right? So here, 5, we have 7 to do here. And now here we can try also 1, and try 2, and try 5. And here we can try 1, 2, and 5. So you get the idea. Every time, what's important here is this x value. So that would be our state. Let's call it the remainder, okay? So the amount left, essentially that's what this is. And the result that the function needs to return, just what the problem asks us, right? Which is the minimum number of coins to make remainder. or x, or whatever you name it, right? And what is the base case? Well, we are done when x is equal to 0. We know we are done, right? So that means here, if x equal to 0, we will need to return 0, right? Why 0? Because there is no more coins to add, right? Now, if for some reason, let's say we are at maybe 3, and then we take coin 5, then that means we are left with -2, right? So we need to handle that case. This is not a kind of a base case, but it's kind of when there is no solution from that point, right? And so for that, we can check if x is less than 0, we can just return something that is a placeholder for no solution, and we can choose, for example, -1. And so now we have these two things. Now what is the recursion that we'll need to do? So this usually what helps is knowing at each point what are the choices that we need to make. And as you can see in what we did here, we just try all coins, right? And just pick the minimum number of coins that each solution will give us, right? And so what this means is, well, what we are looking for is the minimum. So if we call this function, let's say solve with reminder, right? So, or maybe solve, and the parameter, let's call it x. So what this means is that what we are looking for is the min of trying all coins. So that would mean solve for something here for all coins, right? And so what would be the next state once we pick a coin? Well, it would be just, let's see here. Let's put this here because for C in coins. So once we take a coin, let's say here I took 1, well, I did 12 minus 1 to get the remaining number. So this would mean x minus C, the coin value. Now, since I took one coin here, I need to add it to the number of coins I'm using because I used it, right? So +1. And then we take the min of all of them for all coins, and then that's pretty much our solution. And so this is what we'll be trying, what we can use here, right? And so basically just base case, define the state, and define the recursion. And now let's just type this up in a clear way, and then we can optimize it further using memorization later. Okay, so let's see now how can we apply what we just said. So first we need our function, a helper function that we called solve, where we pass the x value. Let's maybe call this amount, and we'll need to call that initially, right, with the entire amount, and we need to return the result for that. And now we need to handle first our base case, which we said is if x is equal to 0, we want to return 0, right? There is no more amount to make. And we want to handle the impossible case when x is less than 0, right? Which we said we will mark it with just -1. And then what we want is to go through each coin. And then we want to try to solve for the subproblem here. Let's call it subproblem. And we only take, one thing I forgot to mention there is we want to only take the amount if it's possible. Like if let's say we have only 2 in the amount left, and we take coin 5, then 2 minus 5 is -3, and that's not useful. So one thing we can do is do it here instead, right? Check if it's bigger than or equal to 0. And then we want to take the min, but we want to have a variable here that keeps track of the min. So let's call it just count. And we will initialize it to any number so that basically the first value that we find here gets set. So to do that, we can just use infinity here. And here we take min of count and 1 plus sub, which is the number of coins, right? And this we'll set that to count. And after we are done, well, we take count, but maybe there is a problem, like we didn't find any value that will give us a valid solution. And so at that point, we'll still have float infinity, right? So to prevent that, we can just say if count is, of course, different than this, then that means we have a solution and return it. Otherwise, just return the thing that represents a no solution for us, which is -1, and so we can just return that. And that's pretty much all there is to this solution here. So let's just run it on an example. So if we do a solution, we'll need to, let's call it on 125 and the amount 12 and run it. We need to print this, so let's print it. And we get 3, which is the minimum we can make. Okay, so now we have our top-down dynamic programming approach. We can use memoization to avoid the fact that, well, maybe we will pass maybe 11, like let's say 5 multiple times, and to get the number of coins for 5, because using different denomination give us a reminder of 5. There is no need to compute that multiple times, and so we would use memoization here to prevent recomputing it multiple times. It's essentially just caching the result. And so to do that, let's just go and create a map. You can also use an array. I'm just going to use a map here. And instead of recomputing, I will check if I already computed it, which means I already put it in my memoization table. And so if I did, then I just return that and do not recompute it again. But if I didn't, I computed, and then before returning, I set the value, and then I returned that. And that's pretty much it. So let's run this again. And we're good. So this is the top-down dynamic programming approach. Now let's look at the bottom-up DP solution for this problem. Okay, so now that we saw the top-down approach, let's now look at the bottom-up approach to solve this problem. So for this, we will just use exactly this problem, except we want to do it in an iterative way. And so essentially here, for this kind of thing, we will need to come up also with a couple of things. For this problem, it would be easier because we already solved it in the simple recursion way here. But usually you could just jump straight into doing it in a bottom-up approach way. Also, some problems when you solve them with the top-down approach, they are slower than with the bottom-up approach. So it's good to know how to do it this way. And so the goal here, you need a couple of things. You need what's the goal, which in our case here, it's the minimum number of coins to make an amount. And then we will need to know what is our state again. So what is the state here? And so in this case, it is just the it's the minimum number of coins to make some amount I, right? So that would be dp of I. This is our dp array, and it would be same thing, min number of coins to make amount, except I, specifically an amount I. Here it's the overall amount, maybe call it X or something. And so after that, we will need to determine what is our base case, right? So our base case is, first we will need to figure out what should we initialize our dp array with. So right away, first we don't know how many coins for a certain amount, so we can just initialize it with something like maybe -1, because that doesn't really exist as a number of coins, right? So maybe we could just initialize it to -1. And in Python, we want to do it for, let's say X is the amount. We want to do it for X plus 1, because the array, to get the last value dp of X, the array size needs to be dp of X X plus 1. The other thing is, the base case here is for dp of 0. So the minimum number of coins to make amount 0 is just 0. You don't need any coins to make 0, right? And now we will need to come up with the recurrence, right? So our recurrence here, we can just, it's very similar to this to the recursion approach one. So basically, for dp of I, we can obtain the value there just by getting the minimum of trying all coins, right? dp of I minus, so minus a coin, plus 1, of course, because we just used this coin, and we try that for all coins. So this is our recurrent solution. Now, what is the order of iteration that we need to do so that when we are trying to compute dp of I, we already have computed dp of I minus c? So that's another thing we need to come up with, which is the order of iteration. So here, in order to get I, we need to have I minus 1 already computed. So right away, we know that we need an increasing order, right? Which basically means we need to start from 0 or 1, because 0 we already used that, to the amount, or maybe whatever the amount is as a parameter, right? And then at the end we can just return dp of amount, right? So this is the result that we'll return at the end. And with this method, pretty much we are done. We know what we need to do, and we can start solving the problem, right? So increasing order here is for I, the amount, and then for each amount we will try all coins. And that's pretty much all we need to do to construct our solution. And so what we will need to do is just take I for the overall result in the range of amount plus 1 to be able to get to the final amount, right? And then for each one we will try all coins, and then we'll just apply the recurrence, which is dp of I equal to the min that we have so far of dp of I, and then plus 1 plus dp of using that coin, right? And then at the end we'll return just dp of amount. So a direct application of what we just described. And now let's type this up and see and just see it, see how it works. Okay, so next let's implement this solution here using bottom-up dynamic programming. So we will need to have the same method signature, and then we'll need to initialize our dp of array, which we said it would be. We just initialize it with this, and we need amount plus 1, and then we have our base case, which is for dp0, and then we want to go for I, we want to try all until amount, right? And then we want to try every coin, and essentially just say if, well, we can just say dp of I equal to min of dp of I, and then 1 plus dp of I minus, so using basically that coin, which is I minus c, and then we used a coin, so plus 1. Here we can do something which is, just to make sure we don't get minus 1 in this dp array, which would be very wrong, we can just make sure that I minus c is bigger or equal to 0, which is also the same as saying I is bigger or equal than the coin value, right? And then after that, we want to return dp of amount if the value of that is different than minus 1, right? Otherwise, well, actually we can just return dp of amount, because if it's minus 1, then we'll return minus 1 as the solution, which just represents the fact that there is no solution, right? And that's pretty much it. So right now we can see what this gives us. So we get minus 1, which is very wrong here. So yeah, the problem is min here will pick minus 1 always, because that's the smallest value. So we want something that will make any value be smaller, and so that is just float of infinity, right? And that's 3. But the problem here is that if this value is not there is no solution, we'll get infinity, and that's not what we want. So what we can do for that is basically, if dp of amount is different than this, then we return it. Otherwise we just return minus 1, so that we can mark the fact that there is no solution. And yeah, that's pretty much it for this bottom-up dynamic programming solution. Okay, so another thing that we might be asked is, well, what are the coins that we used for a solution? Here we just return the number of coins that we have used. How can we just take this solution here and be able to return the number of coins that we used, right? To return just the coins themselves, right? So how to do that? So all we need to do is just here, when we take a solution, when we take a coin, just basically save that, because that's what we want, right? And so what that would mean here is we can just keep track of an array that shows us the coins that we used, right? So we initialize it to 0 first for amount plus 1, same thing as the DP table. And then here, instead of doing this min here, we want to know exactly when we are taking a coin. And so we take a coin when we know it's smaller, right? And so to do that, we will just check if dp of I is actually bigger than, basically checking if this taking the coin gives us a better solution. And that would be just checking that this is less than dp of I. If that's the case, that means what we need to do is set dp of I to be instead 1 plus dp of I minus c. So this will do the exact same thing as this min instruction here. And then from there we can, so one thing we can do is we don't need these two if loops, we can just make this with end. And then now we can say that we used the coin, right? For I amount, we started with the coin C. And since now we know that we started with the coin C, so here I will return instead the coins used. And so what that means here is that I will need to say if I have a solution, which means basically that it's different than the infinity, then that means I have a solution. And so I will just initialize an array here that will contain the coins that I'm using, and that way I would return here. And here I will just, while the amount is bigger than 0, I will keep subtracting the used amount, the used coin for that amount. And then I would just add the coins that I used, which is in the value amount. So what this will do, for example, for 12, is that it will give us the first used coin for 12, and then it will subtract that from 12. So let's say it was 5. Then 12 minus 5, we have 7 remaining. And so again, we get the used coin for 7, and that would be 5 again. And then we'll subtract that from 7, we get 2. And then we get the coin used for 2, which is 2. And that way we get the solution. So here, if I print this, so here, if I just print this, I'm gonna, actually not this, sorry. So you can see here we have 2 and 5 and 5. These are the solutions. Now let's just try with a couple more examples. So let's try here with this example. So you can see for 11 we get 155. For 2 there is no way to do it, so we return an empty list. For 100 we can use the best ways to use all 5 coins. And all coins of denomination 5 essentially, and that's pretty much it. And this is usually how we solve for or at least most of the time we just need an extra array to keep track of the solutions that we are using for a dynamic programming solution. Yeah, so I think that's it now for this problem, for the coin change problem. Thanks for watching, and see you next time. Bye.